Okay, for doing conservation of energy with rotating objects, uh, let's just make sure we understand what's going on. The kinetic energy of an object that is just moving, we know the formula for that. It's 1/2 mass times velocity squared. So that's if we have just a moving object. If we have an object that's just rotating, then the kinetic energy is 1/2 times the moment of inertia times the angular velocity squared. So this would work if I had a object that's rotating around a pivot like that, or if I had a ball that's just rotating around its center, or if I had a plate that's rotating around its center, then I can calculate the kinetic energy as 1/2 I omega squared. Okay, so what if we have an object that is both moving and rotating? Imagine like a baseball flying through the air with spin on it. Well, it has both kinds of kinetic energy. So then the total kinetic energy of this object would be 1/2 m v squared plus 1/2 I omega squared. And there are a couple of little pieces we need to be sure we're a little careful of when we have this situation. So the first piece is that this ball, I don't know if you can imagine this, but if the ball is moving forward and the top of the ball is rotating forward, and the bottom of the ball is rotating backwards, then the top of the ball is moving forward faster than the bottom of the ball. And of course, the front of the ball is moving down, and the back of the ball is moving up. So what velocity are we actually talking about here? Well, the velocity that we need in the formula is how fast the whole ball is moving, which is also considered like the center of mass velocity. That is, if you just think of the ball as like a point at its center, how fast is the ball moving? Okay, and then also when calculating the moment of inertia, we're going to calculate the moment of inertia around the center of the object. So we're going to treat it as if it's rotating around its center. So we can calculate the kinetic energy of an object that's both moving and rotating by calculating 1/2 mv squared plus 1/2 I omega squared. Okay, and so you can imagine that. Now, there is sort of two sort of special conditions. The first one is if we have a ball or a wheel or any sort of circular object that is rolling on the ground. Now, you can imagine if it was just spinning and not moving anywhere, it's like the wheels would be skidding, right? It'd be like like doing a burnout. Or if it was just moving and not spinning, oops, then it would also be skidding across the ground. It'd be sliding across the ground. But if it's rolling, then it's going to be both moving forward and rotating. And in fact, the speed that it's rotating and the speed that it's moving, if it's rolling on the ground perfectly without doing any skidding at all, that's called rolling without slipping. And in that special condition, we know that the angular velocity of the object is equal to the velocity of the center of that object divided by the radius of the ball or the wheel or whatever it is. And we also know that the angular acceleration, if this thing is speeding up or slowing down, is equal to the acceleration of the object divided by the radius of the wheel. So that's an important relationship when we have an object that's rolling without slipping is that we know it can't just have any old angular velocity and velocity. The two have to be matched to each other. Okay, and that is similar to if we have a pulley and we have a string wrapped around the pulley. If that string is moving with a velocity v, the pulley has to be rotating, okay? And we get the same relationship. The angular velocity of the pulley is equal to the velocity of the rope or the string divided by the radius of the pulley. And the angular acceleration of the pulley is equal to the acceleration of the rope divided by the radius of the pulley. So those are both really important kinds of relationships that can show up in problems. But a really important thing about rolling without slipping is when we're rolling without slipping and we're thinking about energy, we usually are safe using the approximation because there's no skidding happening between the wheel and the ground. There's no thermal energy being created. So when we're rolling without slipping, it is usually a good approximation to say that the change in other kinds of energy is equal to zero. That is, no thermal energy. Now, it's not really no friction, because there is actually friction. It's just that there's no sliding happening between the ground and the ball, so that friction creates no thermal energy. So rolling without slipping is sort of a special situation that gives us a hint that we could use the conservation of energy equation and use the fact that the change in thermal energy is going to be very small when we're rolling without slipping. It's not exactly zero, but it's a good approximation to say that the change in thermal energy is zero when you've got an object that's rolling without slipping. Okay, so let's. Yep. I did have one more thing I wanted to say about energy problems, and that is if we have a problem where we have an object, let's say we've got a ball, and we've got a hinge on this ball that's down at the bottom. And of course, if it's balanced perfectly, it could stay there. But if it just off balance a little bit, what's going to happen is this thing's going to start rotating around that pivot. Okay? And so as it rotates around, right, it's going to end up here at the bottom. Okay, that's not a very good picture, but it's going to end up there at the bottom. And it's important to remember. Now, what we would do in this situation is we would use conservation of energy. We would say, okay, the kinetic energy at the beginning plus the potential energy at the beginning is equal to the kinetic energy at the end plus the potential energy at the end plus the change in other kinds of energy. And we're going to use energy because we're going to assume there's no air resistance, and we're going to assume that there's no friction, and so that ball is basically like an isolated system. The ball and the hinge together make an isolated system. Well, with the Earth, of course, because we've got gravity. So the ball and the Earth together make an isolated system, and so we can use the conservation of energy. And so we'd say, okay, well, at the beginning it's not moving, so the kinetic energy is zero. And at the end, this thing's, at the bottom, so the potential energy is zero. We already said that the change in other kinds of energy is zero because there's no friction, there's no air resistance. So that leaves us with potential energy, mg y initial, is equal to kinetic energy final, 1/2 I omega squared. This thing's just rotating, so there's no 1/2 mv squared. There's just 1/2 I omega squared. Okay, but the trick is, what's the initial height and what's the final height? What we have to do is measure the center of mass of these objects. So the center of mass is right here. So I'm going to label that as y equals 0 at the bottom. So then how high is this ball when it's at the top? Well, in this case, we've got the radius of the ball here, and we've got another radius of the ball there, so it looks like y initial is equal to 2 times the radius of the ball. But notice what we don't want to do is measure from the bottom of the ball to the top of the ball or whatever. We want to measure from where the center of the ball starts to where the center of the ball finishes when we're measuring the change in height. Okay, so when we're doing gravitational potential energy for objects, we always measure to the center of mass of the object. All right, I think that's enough for now.